Good afternoon or good morning or good evening, whenever you intend to watch this. Today, though, is November 13th. It's actually Friday the 13th. And we in class today have finished off assignment number 8 as far as having finished the class-wide kind of stuff. Now, before we get into it, I do want to make a couple of announcements and make sure we're all up to date as far as that's concerned. First thing, just looking forward uh, to the rest of the year. At this point in time, there are almost 4 weeks left. Um, Breaking that down into days, essentially, every period has about 10 days left of class. What this means as far as the rest of the year is concerned, what we're looking at is off to the side here. This is going to be our timeline. Come Monday next week, we'll finish off our notes on thermal energy and then get started into the flow of energy and try to finish that next week before Thanksgiving break. Coming back from Thanksgiving break, we'll either wrap up the diffusion of energy or we'll start talking about entropy, which is a real fun topic if you're kind of a downer. From entropy, we'll start on assignment 10, and this will take us to the third week here. It'll take us to the 7th, I suppose. So we'll either finish off assignment 10 as we head into December and get started off on work and heat and Earth's interior. And that'll wrap up sometime around the 10th or the 9th, around then. That's what I suspect. That leaves the last 1, 2, 3 days for our final, which is to make a model of Earth that will let us predict a few properties. We'll get to that when we get to that. We'll pause and wait for there. Now, as far as the rest of the year is concerned, we were supposed to have a quiz. I've nixed it in favor of being able to spend a week on our final and having you guys make your models. A little bit of that crunch time coming in, so suspect that our final will be released around the time we work on assignment 10. Okay, now as far as Friday is concerned, as far as Friday, November 13th is concerned, we're done with that. As far as that's concerned, I am collecting assignment 7 today. Make sure you have all 3 graphs filled out. You have those answers highlighted as we have it here. We did do this as a class, so there's no reason for it to not be filled in. And then you are supposed to answer the predictions part on your own, as well as the conclusions section on your own. So that kind of brings us back to assignment number 8. And so recall that this entire time we've been talking about heat. How does heat affect gases? How does heat change the temperature? How does heat change the pressure, change the volume? Those are those 3 main topics we're working with. And so last time around, we went through numbers 1 through 5, so I'm not going to go through that. I'm going to work on number 6 through 8. And I say I'm going to work on, I'm not really going to work on it. I'm going to go over what we did in class. So what we did in class was we matched the graphs to the correct equation below. So we'd select it, press edit. We could, draw in lines that match our graph. Now, the big thing I want to show us here is that these graphs, right, are pressure versus volume. So we want to make sure the variables are correct. So we have volume here and pressure here. Something we didn't really, something that a student acknowledged, and I actually didn't really consider, was that recall that if you have a linear line, like a straight line like this, your equation is going to be straightforward, right? It's just a one-to-one kind of thing. And that's what you see here and here. It's a one-to-one thing. If volume increases, so does temperature. Now this graph is curved, and so therefore the only equation with the curve in it is going to have that 1/2 kind of symbol. Now, how do we get these laws? And so the idea is if I have a balloon, right? Let's say I have a balloon. Actually, let me go back a bit. So we're trying to relate volume, pressure, and temperature to each other. Each time we do that, one of those kind of has to sit out, right? Because if we're talking about volume and pressure, then temperature is sitting out. If we're talking about volume and temperature, pressure sits out. If we're talking about pressure and temperature, then volume sits out. So every single time we have 3 variables, one of them always has to kind of sit out. And so that one that sits out is our constant, letter K. And so what we did as scientists, we try to isolate K, get K by itself. And so if we do that, we have pressure and volume is equal to that constant temperature. And so what that means is, let's say I have a balloon and I'm squeezing down on that balloon. I tighten it up. Now my pressure is very high, my volume is very low, but the temperature, let's just say, is 25 degrees. I let go of the balloon. The pressure is gone. The pressure decreased, but my volume went up now because there's less things holding it in. I've got a big balloon, but the temperature never changed. And so if the temperature never changed, now we could relate the pressure and volume at two different points to each other. So we have our pressure and volume at one point versus the pressure and the volume at a second point, and those two things should be equal. And that's the basis for these equations. We're essentially comparing these variables at different points in time. Now, normally I would spend much more time on these equations, but new book, new standards, less of an emphasis on the math. I would normally spend like a week on gas laws, but less emphasis on the math and more importance on the idea of that relationship, right? Volume pressure relationship, the volume temperature, pressure temperature, those relationships. So less emphasis on the math, more of a qualitative kind of information check. That's what we're doing here. So moving on, we're going to work with some math. So number 7, the molar mass of an element is equal to its atomic mass or weight. All 1 molar samples of gases occupy the same amount of space at standard temperature and pressure. And they do this by having, on average, the same amount of kinetic energy, but different amounts of speed. Okay. So this goes back to this kind of image here. So notice we have particles of helium. Let me zoom in here. We got particles of hydrogen gas, oxygen gas, and carbon dioxide. They're all differently sized, differently shaped, but 1 mole of each will always occupy 22.4 liters. And the way they do this is because they all have the same amount of kinetic energy, but different masses, which means that they either fly slower or faster, and that lets us kind of predict how fast these things go. Let's go take a look at periodic tables. And so we have all these elements. We have so many elements, but what we're looking at is the atomic mass, right? That's the large number at the bottom. We have our atomic number here that tells us element number 38 is strontium, and it weighs 87.62 grams per mole. I look at element number 79, that's gold, 196.97 grams per mole. If I look at radium, 226 grams per mole on average. Barium, 137.33 grams per mole. I had lots of jokes about some chemistry stuff, but I kind of had to bury them. Anyway, for our number 7 here, we're looking at helium, neon, xenon, and argon. Again, I had lots of chemistry jokes before, but all the good ones are gone. Anyway, so note that down. We're looking at the atomic masses for helium, neon, argon, and xenon. So we have that written down. Now, what we're doing next is we're going to find the speed of these particles based on several assumptions here. First, we're going to use this equation, the kinetic energy equation, right? So this tells us that the kinetic energy of anything, right, the force that these things make is equal to 1/2 mv squared. M is mass. In this case, we're talking about molar mass specifically. And v is the velocity, the speed, how fast something's going. To talk about the difference between velocity and speed, there is one, but we're going to use them interchangeably here. Just let it be. V is velocity or speed. We're going to calculate the speed of each of these molecules by using this formula. So we're going to do an assumption first. We're going to assume that a kinetic energy is 2.5 million. We're not going to attach any units to that. We're just going to assume it's that number because we just want to practice with this equation. And so 2.5 million equal 1/2 times 4.026. Remember, that's the mass of our helium particle, v squared. So we want to get v by itself, right? Take half of it, divide it by 2, take the square root of both sides, and now we're at 1,118 meters per second. Do the same thing with neon, right? Kinetic energy doesn't change, only the mass changes. Take half of the mass of neon, divide it over to both sides, take the square root of both sides, and now we're at 497, right? And so the pattern here is very straightforward. We have a very small particle and then a very large amount of speed. We have a larger particle and then a smaller amount of speed. You guys have to do argon and xenon on your own. We kind of established the relationship already. The heavier the mass, the slower the speed, and vice versa. The lighter the mass, the faster the speed. And you'll have to do number 8 on your own as well, which is listing the 5 assumptions for an ideal gas. That's just some minor stuff. Have it down for yourself. We'll cover it when we start talking about the flow of energy, especially when it comes to diffusion of gases. All right. And so we kind of get started on the notes, but just to wrap this up, this was the main thing for today, getting the last half of assignment 8 finished. And so in our textbook on page 74, we'll find this chart. This chart's important because it lets us visualize the speed of these particles. So we see here helium, right? Helium right around here. And most helium particles will, some helium particles will be a little bit faster, some will be a little bit slower, but on average, the speed of this is somewhat over 1,000. And that corresponds to what we know. We know that the speed of helium is about 1,118, and so that kind of matches up. We look at neon, and look at that. It's at pretty much at 500. And so again, it matches with what we saw in that equation, right? So the relationship between weight and speed is seen here. The heavier something is typically the slower it's going to get. And so when you do your calculations for argon and xenon, you'll see that, okay, argon is a little bit slower than neon. I might have shifted it a bit. Be closer down here. So it's probably somewhere around the 400 meters per second mark. Xenon, way slower, and I'm not drawing straight lines. It's a little bit less than 250, maybe like 200-ish. And so use this to kind of check your work, to kind of see if your answer corresponds with what you get. That'll be about it. So this took a lot longer in class because, again, I'm asking questions, I'm getting your feedback here. So these videos are a lot faster than what you discuss in class. So if you can't make it to class, try to get to class. Otherwise, these videos are kind of supplementary. Now, one last thing, Unit 1 has been turned in. So 15-week grades have been turned in. But if you still want to update your grades, you still want to do better, you can. You can still turn in late work. Don't let yourself get down. You can still do it. Assignment 7 is due November 13th, the day this video is posted. So work on that. And I'll see you guys in class next week before Thanksgiving break. And I hope you all enjoyed the video. Bye-bye.